Neutron stars are some of the most extreme and violent phenomena in the universe. They are giant atomic nuclei measuring only a few kilometers in diameter, yet possessing the mass of a star. Their existence is owed to the death of something majestic. Stars exist due to a delicate balance. The mass of millions, billions, and trillions of tons of hot plasma is pulled inward by gravity and compressed with such force that nuclei fuse hydrogen into helium. This releases energy that counters gravity and tries to break free. As long as this balance is maintained, stars are relatively stable. However, eventually the hydrogen will be exhausted. Medium-sized stars such as our Sun go through a giant phase where they burn helium into carbon and oxygen before eventually turning into white dwarfs. However, in stars that are many times the mass of our Sun, things become truly interesting. When the helium is exhausted, the balance of pressure and radiation tips and gravity wins, squeezing the star tighter than before. The innermost regions of the star experience intense heat and rapid burning, while the outer layers expand significantly, resulting in the fusion of increasingly heavy elements. Carbon burns to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in a day, then death. Iron is the remnant of nuclear reactions. It lacks the energy to sustain fusion and cannot be fused further. The fusion process abruptly ceases, bringing the reaction to a halt. Without the outward pressure from fusion, the core is crushed by the enormous weight of the star above it. What happens now is both awesome and terrifying. Particles such as electrons and protons typically do not want to be near one another. However, the immense pressure of a collapsing star is so great that these particles fuse together to form neutrons. These neutrons are then compressed together as tightly as they are found in atomic nuclei. As a result, an iron ball the size of the Earth is compressed into a ball of pure nuclear matter the size of a city. However, it is not just the core that implodes. The entire star collapses in on itself. The force of gravity pulls the outer layers in at a staggering 25% of the speed of light. This implosion produces a shockwave that explodes outwards, propelling the rest of the star into space. This is known as a supernova explosion, and it has the ability to outshine entire galaxies. The remains of the star have now transformed into a neutron star. Its mass is around 1 million times that of the Earth, yet it is compressed to an object that is only 25 kilometers wide. This density is so great that the mass of all living humans would fit into just 1 cubic centimeter of neutron star matter. This equates to roughly 1 billion tons in a space the size of a sugar cube, or as another comparison, the mass of Mount Everest in a cup of coffee. From the outside, a neutron star is incredibly extreme. Its gravity is the strongest outside of black holes, and if it were any denser, it would become one. Light is bent around it, allowing for the viewing of both the front and parts of the back. Additionally, the surface temperature of a neutron star reaches a staggering 1 million degrees Celsius, in contrast to our Sun's mere 6,000 degrees. Now, let's take a look inside a neutron star. Although giant atomic nuclei are similar to stars in many ways, they also possess characteristics of planets, such as a solid crust over a liquid core. The crust is incredibly hard, composed of iron left over from a supernova, tightly packed together in a crystal lattice with an ocean of electrons flowing through it. As we delve deeper, gravity compresses the nuclei further, resulting in fewer and fewer protons as they merge into neutrons. Eventually, we reach the base of the crust, where nuclei are squeezed together so tightly that they begin to touch. In this state, protons and neutrons rearrange, forming long cylinders or sheets, which are enormous nuclei with millions of protons and neutrons shaped like spaghetti and lasagna, known as nuclear pasta among physicists. Nuclear pasta is a material that is so dense that it could be the strongest in the universe. It is found in the form of unbreakable lumps inside neutron stars, and can even create mountains that are only a few centimeters high, but are many, many times more massive than the Himalayas. Scientists are not certain about the properties of matter when it is compressed, but some believe that protons and neutrons may dissolve into an ocean of quarks, known as quark-gluon plasma. Others believe that quarks may turn into strange quarks, creating a sort of strange matter with extreme properties. Neutron stars, when first formed, spin very rapidly, creating pulses due to the emission of beams of radio waves from their magnetic fields. These radio pulsars are the most well-known type of neutron star, with around 2,000 known to exist in the Milky Way. The magnetic fields of neutron stars are the strongest in the universe, being quadrillions of times stronger than Earth's. They are known as magnetars until they calm down. The most fascinating kind of neutron stars are those that form binary systems with other neutron stars. These systems emit energy as gravitational waves, ripples in space-time. As their orbits decay, they can eventually collide and explode, releasing heavy nuclei in the process. It is believed that this process is responsible for the creation of many of the heavy elements in the universe, such as gold, uranium, and platinum. When neutron stars eventually collapse into black holes, they bring an end to the elements they created. Over millions of years, these atoms are mixed back into the galaxy, but some end up forming stars and planets, starting the cycle anew. Our solar system is an example of this process, and the elements created by neutron stars that came before us make up our entire world. Neutron stars that were formed eons ago are sending atoms on a 13 billion year journey to come together and create us and our world. This is pretty amazing, wouldn't you say? What's your take on this? Let me know down in the comments below and check out one of these other videos. This has been Mr. Singularity, and I'll see you on the next one.